Okay, let's talk about something truly mind-bending. You know that chair you're sitting on? What if I told you it's basically a giant, stable battery of pure, concentrated energy? Well, it is. And that wild idea comes from one of the most famous equations in all of science. We're going to break down how it totally flipped our understanding of the universe on its head.
So, let's start with a simple question. How in the world do you weigh a single atom? I mean, seriously, it sounds impossible, right? You can't just pop it on a kitchen scale. We're talking about a scale of reality that is just unbelievably tiny.
Just to give you an idea, let's look at a single electron. In kilograms, its mass is, that number. Look at all those zeros. It's a decimal point followed by 30 zeros and then a 9-1. Can you imagine trying to plug that into a calculator over and over? It's a total nightmare. It's not practical at all.
So it's pretty obvious. Our everyday units, like kilograms, just don't work down here. They're way too clunky. It's like trying to measure a grain of sand with a yardstick. Physicists knew they needed a whole new way of talking about this stuff. A new language, really, built specifically for this incredibly small world.
And the solution? Well, it came from an idea that completely changed everything. It wasn't just about inventing a new unit of measurement. No, it was about seeing reality in a whole new way. And it all came from, you guessed it, Albert Einstein.
And here it is, E equals mc squared. We've all seen it, but what does it really mean? It's not just a bunch of letters. It's a statement about the very fabric of the universe. It tells us that energy, E, and mass, m, are fundamentally the same thing. They're just different forms of each other, connected by this huge number, the speed of light squared. Let that sink in for a second. Mass isn't just stuff, and energy isn't just invisible force. They are literally interchangeable. You can turn mass into a burst of energy, and you can take energy and create mass. It's this core idea, this mass-energy equivalence, that unlocked a much, much better way to measure things at the atomic level.
Okay, so on the mass side of the coin, physicists said, forget those kilograms with 30 zeros. Instead, they invented something called the atomic mass unit, which we just call U. It's a unit of mass that's perfectly sized for atoms and protons and neutrons. Suddenly, the numbers become nice and simple and manageable.
And of course, they did the same thing for the energy side. They came up with a new unit called the Mega-electron volt, or MeV. Just like U is tailor-made for atomic mass, MeV is the perfect unit for the little packets of energy you find in the subatomic world. Everything just fits.
All right, let's see how this actually works. Take our friend the electron again. We start with its mass in those awful kilograms. We plug it into E equals mc squared, and we get this tiny, tiny number in joules. Still kind of messy. But then, we convert that to our new energy unit, and boom! It's just 0.511 MeV. So much cleaner. See how much better that is?
And this is where it gets really cool. Because mass and energy are the same thing, we can now create a direct conversion factor between our new units. It's like converting inches to centimeters. Here, one atomic mass unit, or U, is equal to 931.5 MeV of energy. We can just skip the whole E equals mc squared calculation sometimes and use this direct conversion. It's a huge shortcut.
Okay, so that's all great for particles that are just sitting around. But what about when they're moving? And I don't mean just moving, I mean moving fast, like ridiculously, mind-bogglingly fast, getting close to the speed of light. What happens then?
This is where Einstein's ideas get even stranger, if you can believe it. It turns out there isn't just one kind of mass. There's rest mass, that's how much something weighs when it's not moving, but then there's relativistic mass. That's its mass when it's in motion. And here's the kicker. Its relativistic mass actually changes. It's not constant.
Yeah, you heard that right. It's one of the weirdest things in all of physics, but it's true. The faster something moves, the heavier it gets. Think about that. When you push on something to make it go faster, that energy you're adding doesn't just go into speed. Some of it actually turns into more mass.
And of course, there's a formula for this. Don't worry too much about the details, but just look at the bottom part. As the velocity, v, gets closer and closer to the speed of light, c, that whole fraction, v squared over c squared, gets closer to 1. That means the whole bottom part of the equation gets closer to 0. And when you divide by a number that's almost 0, the result gets enormous. The mass shoots up towards infinity.
Now let's be clear. You're not going to get heavier by jogging. This effect is completely unnoticeable at the speeds we live our lives at. It's just tiny. But Inside something like a particle accelerator, where scientists are flinging particles around at over 99% of the speed of light, oh yeah, it's a huge deal. They have to account for it in all their calculations.
So where does that extra mass go? What is it? Well, it's the kinetic energy, the energy of motion. The formula is really simple. A particle's kinetic energy is just its total energy when it's moving minus its energy when it was at rest. That difference, that extra mass you added by making it move, is its kinetic energy. It's a perfect one-to-one conversion.
All right, let's do a quick recap of the big ideas here. First, mass and energy are basically the same thing thanks to E equals mc squared. Second, to make life easier, we use special units for this tiny world: atomic mass units, or U, for mass, and mega-electron volts, or MeV, for energy. And third, the faster something goes, the heavier it gets, and that extra mass is literally its kinetic energy.
But why does any of this actually matter in the real world? Well, here's a huge one: radiation therapy for cancer. Those machines, linear accelerators, they shoot electrons at nearly the speed of light to destroy tumors. To make sure they deliver exactly the right amount of energy to the right spot, doctors and physicists have to calculate how much heavier those electrons get. This isn't just abstract theory, it's physics that saves lives.
So this really changes how you look at the world, doesn't it? Everything you think of as solid stuff is in reality just a tightly packed bundle of energy. It really makes you stop and think. If mass is just condensed energy, what else are we looking at every day that is completely different from what it seems on the surface?